Hello everyone, I'm Jingli from Southwest University of China. Today I will present our work, Intra-page cache update in SLC mode with partial programming in high-density SSD. This presentation has 4 parts. Let me start with the background and motivation part. As we know, NOT flash-based SSDs have been widely applied in multiple storage devices, such as USB, PC, data center, and even high-performance platforms. This is because SSD have the feature of high access performance, low power consumption, and random access. In order to cut down the price per unit, the cell density has been developed. The right figure shows that the density has been developed from SLC into MLC, TLC, even QLC. That means the cell of high-density SSD can store multiple bits. However, the performance and the lifetime reduce with the price cost. Toward this issue, a part of blocks start to use SLC-mode in high-density SSDs. SLC-mode blocks can have the similar performance and endurance as the real SLC block. These blocks usually serve as the cache of high-density SSDs. However, SLC mode cannot solve the space fragmentation issue because the SLC mode page has the same size as the high-density page. For example, the valid data in right figure only have 1.5 page size in total, but this data occupies 3 pages. This is because the right unit of SSD is page. The request whose size is smaller than 1 page should occupy the whole page. So, partial programming is introduced to improve space fragmentation issue. It can perform multiply and programming with different outsides in the same page as shown in the figure. That means it can directly write data in the free space in the same page. But intra-page program disturbance induced by partial programming. That means the previously written data in the same page suffer from the program disturbance. From the figure below, x-axis represents the P cycle and the y-axis means the bit error rate. We can see the error increased after utilizing the partial programming technique. Therefore, the purpose of this work is to eliminate the error caused by in-page program disturbance. And our basic idea is to update request using partial programming in the same page. Let us come back to the upper figure. The update data have been written by partial programming, and the old dirty data has been labeled as invalid data. These data do not need to consider the error issue because they are useless. Thus, the intra-page disturb can be eliminated. On the other hand, a 4 kilobytes request accounts for a major part from the table below. So, it is possible to use partial programming for update requests on the same page. Besides, from the table, update ratio represents different degree. So, another purpose of this work is to how to write data as more as possible in SLC cache. This is the background and motivation part, and next is the detailed design part. In our design, The update request will be programmed in the same page that contains the original dirty data. Then the intra-page disturb can be eliminated. In addition, we also set three-level SLC mode block. They are work block, monitor block, and hot block. The request which appears at the first time will be written into work block, and then update request will be written in the same page. When the block is full, the updated request should be written into the next level block, such as monitor block and hot block. That is to say, hot write data upgrade from the work block into monitor block and the hot block. Finally, the hot write data can be held in SLC cache. On the other hand, cold data should be ejected into high-density blocks region. It will be conducted in the garbage collection. Let us go to the garbage collection design. The traditional garbage collection policy is a greedy policy. It selects the block having least number of invalid page, and our proposed GC policy selects the block having the least value of invalid subpage ratio. The invalid subpage ratio is to measure the code degree of block. A detailed explanation can be found in the paper. In this example, GC candidate B will be selected. After selecting the candidate block, the valid data should be migrated into another free block. There are two principles. First, the code write data should be degraded. That means if the GC candidate is work block, code data should be ejected into high-density blocks. A core data means the data are written only once in this page. Second, the other data will be migrated into the other free work block. So this design can free up the SLC region occupied by code data, and finally hold code data in high-density SSD blocks. This is the design part. Next is the evaluation part. The SSD sim simulator settings and benchmarks are shown in these two tables. A hot write in the table below means the requests are accessed not less than 4 times. These three methods are used into evaluation comparison. First is baseline. It uses fixed SLC mode blocks and does not support partial programming. Second is MGA. It utilizes two-level mapping table to support sub-page level partial programming. Third is our design IPU. It performs the update request in the same page by utilizing partial programming and ejects code write data during GC operation. Then I'll show the evaluation results. The first result is I/O performance. You can see the x-axis represents block I/O traces and 3 methods, and y-axis means normalized I/O response time. The 2 parts of each bar represent write time and read time. The lower the better. Our proposed method of IPU can decrease I/O time by about 12% and 7% compared with baseline and the readable MGA. There are 2 reasons. First is decreasing the read I/O rate induced by partial programming, and the second reason is holding hot data in the SLC cache. Then I'll show the detailed information about these two reasons. As shown in the figure, our proposed method IPU can mitigate more than a half of read error rate induced by in-page program disturbance with partial programming, compared with the related work MGA. Thus, the read performance can be improved because of less ECC decode time. The second reason is present through three-level block utilization. We can find in the figure about 1/3 write served in the hot block, and the performance benefit can be improved by using the SLC cache. And this is the evaluation part, and the detailed information can be found in the paper. The finally is the conclusion. Our proposed method IPU utilize partial programming toward update requests in the same page. It can mitigate program disturbance caused by partial programming. We further propose three-level SLC-mode blocks and the degraded GC policy for SLC-mode blocks. It can hold more hot write data in SLC-mode cache. From evaluation, our proposal method can reduce the I/O latency and the read error rate. Thank you very much. If you have any question, please contact me without hesitation.